All right, good morning, guys. Today we're going to be covering 8.8 power theorems. So the first thing that I want to really talk about with power theorems is what does the word power mean in mathematics? If I'm raising something to a certain power, what am I doing? Well, if I'm raising something to a power, I'd be multiplying. So that's the main topic of today. We're doing the power theorems, so we're going to be doing multiplication theorems within circles. So let's go ahead and get started. First off, we have some tips for power theorems. And again, the first tip is what we just talked about. Power equals product. Any problem that we do with power theorems is all going to deal with multiplication. So multiplication will occur in each and every single problem. The second thing, how do I know when to use this? Well, these power theorems will be used anytime that we're given secant segments, tangent segments, or chords. So there's going to be three different scenarios that you see, and you'll see them on our theorems as we go through each of those. The next tip, stay on the same segment. Anytime that I'm writing up my expressions, I'm going to have one of my segments, segment 1, and I'll set that equal to whatever segment 2 is equal to. So every single equation will have two segments in it, and one side of your equation will be one of your segments with the multiplications. The other segment will also be multiplications. So again, it's going to be set apart from the equal sign, and again, each segment will have one expression for that equation there. And then the last tip that we have is what we are going to use for our expressions. So we're going to focus in on secants and tangents for those tips, not so much for chords. Chords have their own thing. But for secants, anytime that I'm given a secant segment, it will always be equal to the outside portion of the secant segment times the whole segment. If I'm given a tangent segment, that side of the expression would be whatever that tangent segment is raised to the second power. So again, whenever we're looking at these various theorems, first thing that we want to do is identify whether we have secants, tangents, or chords. Once we determine which one we have, we're going to go ahead and plug in our expression. So let's go ahead and see these power theorems. The first one that we have is the chord-chord power theorem. Now it gets its name because we have two chords here. I have chord En, and I have chord SD. The chord-chord power theorem states, if two chords of a circle intersect inside the circle, which we can see here right at point T, then the product of the measures of the segments of one chord segment is equal to the product of the measures of the segments of the other chord. So what that is saying is that if I take ET, this small portion of this chord here, and I multiply it by TN, the other portion of that chord, that will be equal to ST times TD. So again, we're staying on the same segment here, and we're just multiplying. So ET times TN is equal to ST times TD. If I label these with variables, A, B, C, and D, again, we want to stay on the same segment. So I'd have A times B equals C times D. And that's the chord-chord power theorem. Again, if they cross on the inside, stay on the same segment, A times B is equal to stay on the same segment again, C times D. Our next theorem is the tangent-secant power theorem. Of course, we can go ahead and look at this. We see that we have a tangent line here, tangent PT. And then we have a secant segment here, secant RP. So it says, if a tangent segment and a secant segment are drawn from an external point, point P, to a circle, then the square of the measure of the tangent segment, PT, is equal to the product of the measures of the entire secant, RP, and the product of its external part, QP. So again, I square my tangent, and then I multiply my secant, the whole thing, times the outside portion. So if I label these with variables, my tangent is A, and then my secant segment, the interior portion of my secant is B, the exterior portion is C. So therefore, our equation would be tangent squared, A squared, is equal to the whole thing, B plus C, times the outside part, times C. So A squared equals C times B plus C. If you have a tangent secant segment, that is the equation that you'll use. And further again, that's the whole thing, the whole thing times the outside portion. And that's if we have a secant. Again, if we have a tangent, you just square your tangent. The last power theorem that we have is a secant-secant power theorem. And again, if it's a secant, we do the same thing that we do with all the secants. It states, if two secant segments are drawn from an external point to a circle, which we see here, we have secant segments BP and DP, they both have endpoint P, then the product of one secant segment and its external part, BA times AP, is equal to the product of the measures of the other secant segment and its external parts. So it would be equal to the entire segment DP times just the external part CP. So again, if I give it variables, I have A, B, C, and D. Again, secant means that we do outside times the whole thing. So I'd have B times A plus B is equal to D times C plus D. And here's the equation right here. Again, B times A plus B is equal to D times C plus D. Those are the three equations that we'll use. And again, as long as you remember, secant is equal to the outside times the whole thing, and tangent is just squaring that segment, then you'll be good to go with these. So let's go ahead and try some out. Our first sample problem, we need to solve for x. Now, the first thing that I want to look for is what type of segments do we have in the circle? Well, looking at this circle, I see that we have two chords. Again, both endpoints are on the circle, so these are both chords here. And if we have chords, then our rules are that we're going to use the chord-chord power theorem. We're going to stay on the same segment, and we're just going to multiply. So I'm going to have 3 times x is equal to 6 times 2. Of course, 6 times 2 is just 12. 3 times x is 3x. 12 divided by 3 will give us x equals 4. So therefore, this portion of the chord is just 4 units in length. Next, let's go ahead and solve for y. So again, look at what types of segments you have. In this case, we have a secant segment and a chord segment. I did that backwards. Sorry. We have a secant segment and not a chord segment, a tangent segment. I don't know why I said chord, but this is a tangent segment here. And if we have a secant tangent power theorem going on, then of course I'm just going to square my tangent. And for my secant, I'm going to do the outside portion, 2, times the whole thing, 2 plus 16. So again, square the single, square the tangent. And then for your secant, do the whole thing times the outside. That would give us the equation y squared equals 2 times 2 plus 16. Of course, 2 plus 16 is just 18, so y squared is equal to 18 times 2, which is equal to 36. So y squared equals 36. Of course, we want just y, so I need to get rid of my square. And to get rid of that square, I take the square root of both sides. Square root of 36 will leave us with 6. So therefore, y is just equal to 6 here. All right. And our last power theorem sample problem before we do a challenge problem. When we're solving for z, again, the first thing that we want to do is see what types of segments that we have. So if we look here, we see that we have two secant segments. So again, it crosses the circle at 2 unique points for each of these segments, and they share a common endpoint. And if we have a secant segment, then we do the outside portion times the whole thing. So this would give me 3 times z is equal to 4 times 8 plus 4. Well, 8 plus 4 is 12, and 12 times 4 is 48. So 3z equals 48. From there, I just divide both sides by 3 to get z by itself, and that leaves us with z equals 16. So therefore, the length of this entire segment is 16 units. And our final problem of the day. Tangent segment PT measures 8 centimeters. The radius of the circle is 6 centimeters. Find the distance from P to the circle. So let's go ahead and draw this out together. I have a circle here. I have point P that is not on the circle itself. Now I know that segment PT is a tangent segment, and its length is 8 centimeters. I also know that the radius of this circle is 6. But what we want to find is the distance from P to the circle itself. So what if I extended this length of x and I have it go through the center of the circle? Well, since the radius is 6, it would be 6 on either side, which would then make this segment a secant segment. So now I have a secant and a tangent, so I can use the secant-tangent power theorem. So let me go ahead and draw this nicely. Here it is. And with this, we can go ahead and solve for our unknown variable x. So let's go ahead and plug it into our secant-tangent theorem. Our secant-tangent theorem says that we're going to have our tangent squared, 8 squared, is equal to the outside portion x times the whole thing, x plus 6 plus 6. That will leave us with 64 is equal to x plus 12 times x. Now from here, what I do is I distribute through the parentheses. So I take this x and I multiply it through. X times x gives me x squared. X times 12 gives me 12x. And then I just subtracted the 64 to the other side to set the other side equal to 0. So once we do that, we now have a quadratic equation. And if I need to solve for x, because that's the unknown length, then we need to factor. So to factor, what we're going to do is we're going to take our a value and multiply it by our c value. 1 times negative 64 is negative 64. I look for numbers that will add to be my middle term, 12, and multiply it to be my a times c term, negative 64. Listing out all the numbers that multiply to be negative 64, the only two that will add to be positive 12 is negative 4 and positive 16. So once I find those terms, and of course I can keep listing them, there's many more terms than this, but once you find them, you can stop, of course. Once I find my two terms, I'm going to put them in a double bubble. I'm going to have x minus 4 times x plus 16 equals 0. At this point, each bubble gets its own equation. So I have x minus 4 equals 0, x plus 16 equals 0. That will solve and give us x equals positive 4 and x equals negative 16. So that brings us to the question, what is the length from P to the circle? Well, it needs to be a positive answer because it's a distance. So x equals negative 16 doesn't work. It cannot be negative. So therefore, x equals 4 is the only other possible answer. All right, guys, thank you so much for watching today. If you have any questions, please let me know. But have a great rest of your day. Take care, guys. And thank you for watching.